My name is Ryan Chow, and this is Physics 2211 Lab 1 Constant Velocity for Georgia Tech. So the purpose of this lab was to track the movement of an object given constant velocity and to compare it to a computational model. So what we did was we filmed an object rolling with constant velocity across a flat surface, and then we imported that video into Tracker to measure the time and the position of the object. And then we modeled the movement of an object in a computational model, GlowScript, and then we compared the computational model to the tracker using the graphs. Eventually, we saw that the graphs were pretty much similar, just for little deviations in the beginning and the end. So physics concepts and principles used in Lab 1, we have Newton's second law, an object's acceleration is directly proportional to the net force, and which is also force is equal to ma. Position update formula, R final is equal to R initial plus V average delta t. Velocity update, V final is equal to V initial plus F net over M times delta t, and our average velocity formula, which is just the displacement of x over the time elapsed. So our model here, we had a weight that we set on the ground, we put tracker axes there, and then we just pushed it from the left to the right. So we're moving in the positive x direction. And so our system here is our cylindrical weight, and source is the hand, floor, ground, and everything else touching it. There's the first frame, the last frame, and then here's the total video of it. Yeah. Okay, so initial conditions. So in tracker we had t is equal to 0, of course, and then we had our initial position, which was negative 0.006. And this was just because of small errors when I was doing the axes in the center of mass. So just did it a little bit to the left of the center of the axes. But yeah. And then our fnet, of course, is 0, 0, 0. So initial conditions in the computational model. We started at 0, 0, 0, like the ideal position, and our velocity, or here, was our average velocity, which was 0.5077, and this was calculated from our final position plus our initial position divided by 0.633. And then we had time is equal to 0, and delta t is equal to 0.033. And this was because our camera shot at 30 frames per second, meaning that there was 0.0333 seconds between each frame. So tracker data. So we filmed the video, plot each point, like I said before, and tracker calculates the x position for us. So this is where we get the data, and then we also get this graph. So graph that tracker gave us. It's a graph that is in the positive x direction and has a positive slope. So computational model data. So this is how we did the computation and how we get this graph here at the bottom. So while t was less than 0.633, this our fnet was 0, 0, 0, and then our velocity and our position. These are just fancy ways of writing, or our WebPython ways of writing v final is equal to v initial, and our velocity update and position update formulas. So, and then we have at the bottom t is equal to t plus delta t. This is each iteration, so it calculates the position velocity at each iteration. And here we have the graph. This is a result. And as you can see, they are very similar, both graphs that have a positive slope and are moving in the x direction, positive x direction. So our comparison. Here you can see that when we put the graphs together, they're very similar, like here in the middle, but there's just a little deviation at the end and here in the beginning. So what may have caused this? So human error, this is possible. We may have pushed it not straight. And then tracker, which was tracking the center of mass, was difficult, and I think this was the biggest one. Here you can see that the initial frames were extremely hard to see where the object was, so I think this was part of the problem of why this beginning data is so off compared to the computational model. And also environment, which the floor may have not have been even. So what if I rolled from the right to the left? My final position would have just been negative 0.33, and what if I rolled up and down? and then I would have been moving on the x-axis now instead of or on the y-axis, excuse me, instead of the x. So slope would be negative. Net force 0. No. There is not, in a perfect world, yes, there would have been 0 net force, but there's other forces at play, such as air resistance and friction, that cause the net force to be non-zero. So yeah, thank you.